All right, let's start today's lecture. Before we continue, last time we stopped at here, so we're about to start discussing the properties of the operations. But before that, I feel that I am not crystal clear about data cubes and data cuboids. So I would like to spend a little more time to clarify the definitions here. Also, these are kind of related to what we're going to discuss. So I think it's necessary to get things straight before we continue. All right. So I think the main problem is somewhere here. So here, what I want to clarify is the definition of data cube and the cuboids, as well as the lattice of the cuboids. So from the textbook, if we look at the textbook, a data cube is defined by dimensions and facts, just like what we have discussed before. Okay, so this kind of concept, let me see. All right, so in the books, sometimes they refer a specific, it's more like a cuboid to data cube as well. But let's put that aside. So a data cube is defined by dimensions and facts, and a data cube can be viewed as a lattice of the cuboids, which is what you can see in this slide. Okay. So for a particular cuboid, it corresponds to if say we have n dimensions it's d dimensions here. So for each dimension, we have a particular specific level, because the hierarchy structure, for each dimension, we may have more than one levels. So for a specific level on each dimension, we would have a cuboid. For example, here, this one is on, I think this one is on product, city, and month, right? For this data cuboid, and that's why we say the data cube, the n-dimensional data cube, is more like a set of, or the lattice of all the cuboids, So again, remember the cuboids corresponds to a specific level on each dimension. Then you have a data cuboid. Okay, and all the possible data cuboid forms the data cube. However, in the textbook and in these slides, sometimes we refer to a data cuboid as a data cube as well. And in fact, in most cases, this is the most cases. When we talk about data cube, we actually mean a data cuboid. All right. If we take the data cube as the set of all the set of the lattice, the lattice of the possible cuboids, we barely use that definition or that concept. Whenever we say a data cube, in most cases we actually refers to a data cuboid, and it does not matter too much. As long as you can distinguish these two concepts. And it is okay to use data cube in most cases. Okay, people can understand. The other thing is here, if we say the n-dimensional cuboid, or k-dimensional cuboid, let's say. Right. So this k describes the number of dimensions. You can you can understand and memorize in this way. So it has nothing to do with the hierarchy structure of that dimension. I mean, when we talk about a k-dimension cuboid, the only thing we care is which dimension or which dimensions have do we use to build the cuboids. That's why, I mean, for example, we have 3 dimensions in this example: product, quarter, and country. If we take, if we consider a 2-dimensional cuboid, then it means we take any 2 of them. That's why we have 3 possible cuboids in this case. All right, and also that is why. Let me see. We need to distinguish this concept with the computation here, right? So a complete cube of d dimensions consists of this many cuboids. So the number here, of course, shouldn't be 4 if you mix these 2 things together, because this is the instances of the number of instances of the cuboids, and this is kind of the types of the cuboid. All right. So as we now consider a complete cube is consists of this many cuboids. Actually, in all these examples in during the lectures in these weeks, we actually talks about the cuboids rather than a complete data cube. Okay, so for in many cases we just call it data cube, but it is not a complete data cube. It's more like instance or data cuboids. Okay. So if we go back to here, the properties of operations. All operations are closed, and these operations are here it's actually it should be a cuboid. All right. Or say not, at least it's not a complete data cube, right? So the input and output of an operation is a cuboid. But from now on, we will say cube for most cases. Just to remember, it does not refer to a complete data cube. So before we look at the specific operations, I think it's better to introduce a little bit more about the measures first, because as you will see later, all these, not all, I guess, most of these operations involves aggregation, data aggregation. Okay. In previous slides, we almost always use sum as the example, because it's the most intuitive measurement here. But in real applications, there could be other kind of measures or aggregation functions. Okay. For example, sometimes we use count, right? Sometimes we use average. Sometimes we use median. So they serve different purposes, and they all have their own mathematic meanings, and can help under different scenarios. All right, but they're kind of different in terms of implementation, and of course, I mean, in terms of the concepts, but more importantly, when we do the implementation, they actually brings different difficulties, and although we're not going to discuss the implementation in depth, but it is still meaningful to discuss this before we look at the specific operations. All right. So there are mainly three categories: distributive, algebraic, and holistic. Okay. So the definition of these three categories are listed in these slides. For distributive, say if the result derived by applying the function to n aggregate values is the same as that derived by applying the function on all the data without partitioning. This means, for example, if we do count, say if the data is D, and if we partition the data into D1, D2, and D3, so three subsets or three partitions, if we apply count on D, it's actually the same as count on D1 plus count on D2 plus count on D3, right? So we can perform such kind of aggregating functions, not on the whole data set or the data cube, but on each and every partition, and then do the aggregation, right? And for sum is similar. For min and max, here the aggregate function of the result on different partitions are different. I mean, for count and sum, we actually sum up the values that derived based on different partitions. But for min and max, we actually apply min and or max again on these values that derived on those partitions, right? For example, in this case, minimum of D actually is minimum of D1, minimum of D2, and minimum of D3, right? It is meaningless if we sum these three values together, right? We should use the minimum function. So this is distributive. You can apply the function on a whole data set or the data cube, but you can also apply them on different partitions and then do the aggregation. Algebraic, so if it can be computed by an algebraic function with m argument, where m is a bounded integer, this bounded property is very important compared to the holistic one, okay? And each of which is obtained by applying a distributive aggregate function. Okay, for example, if we do average, it's actually equals to sum divided by count. Sorry. Right? So if we do a sum over count, then we get the average. While both sum and count are distributive aggregate function, right? And it's actually a algebraic function with two arguments. And for minimum n, which is the n smallest elements within a set, or a standard derivation, they all have the same property. Okay, so this is algebraic. And for holistic, if there is no constant bound on the storage size needed to describe a sub-aggregate, then it is holistic. So this means, I mean, there is no algebraic function with m argument because m is unbounded in this case. In this case, right? As the example, I mean, for example, median, we have to know, or we have to have the whole data cube data. Then we can have the median value. Okay. That's why it's called holistic. It's called holistic. All right. So we will still use sum as the measure in most cases in the following slides. But just to I just hope you could keep this in mind. I mean, there are different measures, and they actually have different difficulties when do the implementation. As apparently, I mean, distributive is the most, that is the easiest one, and the holistic is the most difficult one, right? And all right, so there are 4 common operations in OLAP: roll up, drill down, dice and slice and dice. That is basically one operation, and pivot. Okay, so let's have a look of them one by one. So start from roll up. So roll up is to move up the hierarchy. So this operation performs aggregation on a data cube, right? For example, in the next slide, yeah. So we have 3 dimensions: product, location, and time. Okay, and currently for product, we take product. We take product, a level product. For location, we take city as the current level, and for time, we take month as the current level. All right. So now, if we want to do a roll up, say if we want to know not by month, now we now have the number by, or the measure by product, by city, and by month. Right. Now, what if we now want something to be by product, by city, and say by quarter, right? Then essentially we need to climb up one level on this time dimension, right? And how do we do that? We need to aggregate the numbers within different months and to form a quarter, right? To get the numbers for each and every quarter, because we know for one quarter it corresponds to 3 months, right? So this is one way to do the one case of the roll up, and another case is we call it dimension reduction. Say now we have we have 3 dimensions: product, location, and time. We can actually remove this time dimension, right? Which means we will do the aggregation on all the on this time dimension, right? And then we will get the result, or say the measure, by different product and by different cities. But we have already do the aggregation on time. Or the reason we call it we still call it a roll up is because essentially what we're doing is to climb up the time dimension from quarter to all. Right? All is the top level for each and every dimension. So basically we just climb to the top level. Right? Then we get the result. So that is roll up, and the opposite operation of roll up is drill down. It's or say the reverse operation of roll up is drill down. So in roll up, we climb up one or more levels within that hierarchy of specific dimension. So in drill down, we do the opposite. Right? We move down the hierarchy, right? And of course, I mean this involves in getting more detailed data, right? Because for example, we drill down from say quarter to month, then we need to have the to obtain the data for each month, right? And similar to roll up, we can also perform drill. So drill down can also means adding a new dimension within the current data cube, right? For example, if say we currently only have the product and the location, because time is the level of the time dimension is all, so it will not reflect it on the data cube. We will have a 2D data cube, and then if we do the drill down operation, we can actually add time back to the data cube, right? And have a 3-dimension data cube as a result. So this is drill down. And slice and dice. So slice and dice is the operation that select and project on one or more dimensions, dimension values. For example, currently we have 3 dimensions: product, month, and city. If we do the slice, we want to take the information about this specific product, book 176, on different months and different city, the sales, for example, on different months and cities. Then what we do is slice. So we kind of select on one dimension. This is slice. For dice, we do the project on more dimension values. For example, if we want to have, say, the sales data on this specific product, and on, for example, on March, then what we will have, of course, in different cities, then you can imagine what we have eventually is such kind of cube. It is still a cube, but have only one dimension, right? So a cube, something like this. So this is dice, and of course, I mean we can dice to a 0-dimension cube. So for slice and dice, apparently it will reduce the dimension. So what's the difference between, let's say, slice and roll up? Because roll up also can do the dimension reduction. But in roll up, when we do the dimension reduction, we actually do the aggregation, right? Because we need to climb up to from quarter to all. We do the aggregation over all the data on the time dimension, right? But when do a slice, we just select this piece of data with a specific value of this product dimension, rather than do the aggregation. So that is the difference between slice or dice and say roll up. Right, so of course, I mean the output cube has smaller dimensionality than the input cube. Always have the smaller dimensionality, because even for size we need to select one dimension values, So definitely the dimensionality would be reduced by 1. Okay, so the next operation is pivoting. So there are 2 kinds of pivoting. One is on the textbook, one is on this slide. So let's start with the one on the slide. So basically, the pivoting is that it's kind of an operation. It's kind of a visualization operation. So it's help you to visualize the data, right? And by when we say visualizing the data, arguably, 2-dimension is the best way of visualizing data, because even for 3-dimensional, data, you are not able to see, for example, the inner cells. For example, the cell here, you can't see it. All you can see is those cells within the surface of the cube, even it is a 3D cube. But for 2D cube, which is actually a table or something, you can actually view all the values, right? So 2 dimensions is arguably a much better way to visualize the data. Therefore, by doing pivoting, what we want is to select 2 dimensions, right, and to aggregate the data on other dimensions. Then we can visualize the whole data cube. Right, that is our goal. For example, say here we have 3 dimensions: the month. We have the month. We have the cities. We have the products. We have the months, right? And say if we want to select, say, months and cities, then what we want to have is a 2D cube. It is still a cube because it is a closed form operation. A 2D cube, which looks like the first this slides on the top of the data cube, but it is not, because we need to do the aggregation. If we only take, say, the first layer, right, then we will lose the information in the following layer. If we take this layer, we will lose the information in the rest layers. So what we do is we apply an aggregate function. Then we sort of gain the information over the whole data cube, or for each dimension. I mean, over this whole dimension, to reflect it on a new layer, with 2 dimensions, city and month, right? And for this aggregate function, of course, I mean, in our examples we usually use sum, but you can imagine, I mean, it really depends on the application, or because it is a visualization operation, it depends on the end user's needs, right? For example, the end user want to know the maximum value, then you apply a max, right? If the end user want to know the median, then you apply the median. It depends on the needs of the end user, right? But what you do is to take these 2 dimensions and do the aggregation on the rest of dimensions. Always remember that, right? So yeah, so for each cell, because this is what we do if we do this pivot on city and month, we will have a 2-dimensional data cube like this, and for each cell, this is how we get the number for each cell if we want to have the sum, for example, the total sales, right? Then it's the sales of all products in New York, because in the city dimension it's New York. In month dimension, the corresponding value is Q1. So in New York and in Q1. So this is the first type of pivoting. Again, I mean, using three-dimensional case as the example is more intuitive, but it can definitely extend it to more to higher dimensional data cubes. Right? And another pivoting is much easier. It is just the rotation of the data, right? For example, say if assume this is what we have for now, right? And we want to do the pivot. We want to rotate the row and column. Currently, the row is city and the column is month. But if we do the rotation, we will have the row is month and the column is city is cities. Okay. So essentially, it offers you another way to view the data and maybe operate the data. I mean, in relational database, row and column, they actually have their own meanings, and so rows are the transactions, and the column represents the schema of the data, or the attributes. But in data cube or in data warehousing, this row of row and column are not that different. So that's why you can sort of rotate them or change the view by doing pivoting. Okay. So these are the so far these are the four major operations in on data cubes. Okay, and there are also some other operations that are supported by different data warehousing systems or implementations. We won't discuss them in this class, but if you are interested, I mean, you can read the textbook. There is a small list. Okay. All right. So what we have been discussed about data cube mainly is about how to model the data. So if you want to test your understanding, here is an exercise for you. I mean, I do encourage you to discuss this kind of open questions along with other open questions during this class on the forum. Okay, and so I will leave this for yourself, but just to emphasize again, I mean, all we have discussed is about modeling the data, modeling a data warehouse or modeling a data cube, right? And the reason we do that is because we have the data, okay, the transaction data usually. But if we don't do the analysis on the data, then the data itself is meaningless, right? And in order to analyze the data, the traditional relational database, which is transaction based, is not that helpful, right? That's why we have this data cube or data warehousing, the OLAP model. Okay, and in order to model such kind of a data cube, we need to know what is the fact, what is the measure, what are the dimensions. Okay, and for the dimensions, what are the hierarchies for each dimension? What is the hierarchy for each dimension? Right. So as long as you can list or you can answer these questions, you kind of have modeled this data cube. All right. Okay, so what we have been discussed before is like on the conceptual level. Okay, it's on the conceptual level, and now we will start to consider how to do the implementation. So we will start from the logical level. So it's a logical model of data warehouse. Okay, and for the logical models, there are two main approaches. One is using a relational database technology. One is to use multi-dimensional technology. Right. So for those based on relational database technology, we will introduce or discuss star schema and some of its variants. And for multi-dimensional technology, it is just as the multi-dimensional data cube, which we have been discussed before. All right. So yeah, the relational database based technology. Okay. Now, before we go to the star schema, let's look at a simpler case, which is the universal schema. So the universal schema is like a table to take the record of each and every transactions, and for the columns, all the possible attributes or all the attributes, all the possible attributes of that fact, of that transaction. Okay, and it is just like a very basic. So this concept actually appears in the relational database, traditional relational database as well. I mean, if you know functional dependency, so basically, if we have this kind of a universal schema, this whole large table or as the records of all the transactions, and if we apply a functional dependency and some constraint, we can actually decompose it into several tables, and to to better reflect the relation between the attributes, as well as to save some space. Okay, we will see how to save the space or make things more clear later in the next slides. But so here, even from this example, I mean, it's kind of straightforward for everyone to figure out a possible way to do the decomposition. So basically, this store city. So this store, city, and state, they all belongs to a location information or a location dimension, if you like. And this product, brand, and category, of course, it belongs to a dimension, maybe called product or something. Okay, and this dollar sold, number sold, cost is more like so this is more like the facts, okay, the real parts of the transaction, all the measures. Okay, other parts is more like the dimensions. Now, so apparently we can decompose it into 3 subtables, right? And if we do so, for example, we can take a store, city, and state as in one table, right? And product, brand, category in another table, and so on and so forth. And if we do that, for example, here, we do not need to record 2 records here because they are identical within this subtable. Okay, so by doing so, we can kind of save the space. But for the third one, we cannot only record dollar sold, number sold, and cost, because we need to know which store, so information about the location, and which product, which is the information of the product. We need to know them, right? So we kind of have to put these two columns together with these three to form the last table. Okay, and if you still remember, I mean, in relational database, it's actually called a foreign key. Okay, so these are the primary key of the location table and the product table, and they're also the foreign key of this fact table, or it's actually called fact table. Okay. So many data warehouses adopt a star schema to represent the multi-dimensional model. Each dimension is represented by a dimension table. Okay, so each dimension is represented by a dimension table. And transactions are described through a fact table. Transactions are described through a fact table. And here, I mean, each tuple consists of a logical pointer to each of the dimension tables, all right, as the foreign keys, and a list of measures like the dollar sale. So we will we will see an example first, and then we go back to to explain this in more detail. Okay. So this is an example of a star schema, and apparently this table, the sales, records all the transactions. So it's like a fact table, if you like. And all the others, product, location, and time, apparently they are dimension tables. They're dimension tables. So for the fact table, we have a time key, which is a foreign key, right? Point to the time key here in the time table, right? Where time key is actually a primary key. And a product key is the foreign key point to product table, and a location key is the foreign key point to the location table. Okay. So for each dimension, we have one foreign key. And for say for the rest of this fact table are the measures. Right? So we have two measures here: the units sold and the amount. So these are the measures that we care about. So these are the measures. These are the foreign keys. And for each and every dimension table, we have a primary key. Right? This is the primary key. This is the primary key. All right. And for the rest part of each and every dimension table, it's actually corresponds to the levels on the hierarchy of that dimension. Right? For example, if we take the time table here, right? We have day of the week, month, quarter, and year. So the hierarchy would be day, right? And month, quarter, and year. Okay. And also there is another hierarchy is day of the week. Okay. And if we consider the all should be here. Right? Although all it will not be in this dimension table. Right? So if we look back, the dimension tables are not normalized, right? Each dimension is represented by a dimension table, and the dimension tables are not normalized. We don't further normalize a dimensional, we don't further normalize a dimension table, okay? And we only do one normalize to have the dimension tables. Let's see if I can give you an example here. Yeah, for example, if we consider, say if we consider store, city, state, and country, right? So if we have a store A1, A2, A3, so on and so forth, and say if the city is Sydney, this is Sydney again, Sydney the third time, and so on and so forth. So the state would be the same, okay? And of course, the country would be Australia always. So the idea here is that, in fact, this kind of table can we can further decompose it or do the normalization on it, because we have we know that as long as the city is Sydney, the state should be NSW and the country should be Australia. Okay, so we can actually have another table record this say sorry, the other table should be city, state, and country, where city is the primary key, and we take city as the foreign key here, so we don't need to store the state and country redundantly. Okay, this is typically what we do in relational database. Right? We want to have a better functional dependency. We want to have a better norm. Okay. However, in data warehouse, we do not further normalize a dimension table. Okay. As for the reason, I mean, it's not like we cannot do this. Right? My understanding is that it's more like a trade-off. A trade-off between space and efficiency. So if we do the normalization again and again, of course we will save some space, but what we need to pay is more time and more computational cost when we do the query. And compared to the space that we have saved, which later hopefully I could show you a little bit more, it's simply not worth it. It's simply not worth it. Also, I mean, it makes the things more complex. So we don't. It's more like a recommendation. I mean, it's not a real rule or whatever. I mean, of course you can do the normalization again, and the system may still work, or even the system does not defaultly support such kind of operation. I mean, you can easily implement it by yourself, but it's not the best way to do it, considering this kind of time-space trade-off. All right. So this is for the dimension table. Fact table, transactions are described through a fact table, right? And each tuple consists of a logical pointer to each of the dimension tables and a list of measures, right? So which are the foreign keys, right? The pointer to each of the dimension tables and the measures. So when you draw such kind of star schema, always remember, I mean, we probably have such kind of questions in the exam or in the assignment. So for the you need to know what is the factor table and what are the dimension tables. Also, how many dimension tables are you going to have? I mean, it depends on how you model the problem, of course. But also remember, for one dimension, you should have just one dimension table. And for the factor table, it is there are two parts, right? One is the foreign keys point to the dimension tables, and the other part is the measures. So what are the advantage of this kind of star schema, right? What does it do? So let's start from the transactions or the fact tables. So if we consider the universal schema, say the number of columns of the universal schema should in general be the sum of the sum of number of columns in the dimension tables plus the number of measures in the fact table. All right. And in this case, it should be it's 6 here, it's 7 here, it's 6 here. So it should be 21. Okay, it should be 21. So for a universal table, it should have 21 columns. And how many rows? Because each row represents a transaction. Each row represents a transaction. And if we take, let's say we're trying to model the sales in, I don't know, Woolworths, for example, then you can imagine even in a month. Yeah, I probably should I should Google the number here. Just give me 1 minute. So I did a quick Google search. I don't know if the number is for per week or per year, but it's 1.6 billion. Okay. I think it's maybe even per week. I mean, per year, suppose should be much larger than that. But even 1.6 billion, it's a real large number. It's a real large number, and you can think how many storage do you need to store such this much data. But if we do this star schema, okay, for the fact table, we have 1.6 billion transactions, but we only have 5 attributes here, 5 columns here. No matter, not mention, I mean, storing a key should be much should take much less space than store a string, for example, for the product name or address, a street address or something. Okay, we ignore that. We only have 5 columns here. And for the location, yeah, just as I Googled before, they have about 3,000 shops within Australia. So means for location, we would have 3,000 records at most, and we have this 7 columns. Okay. For product, let me see if I can find the number. Well, it's not easy to get a specific number within this short time, but I mean, we can guess. We can make a guess, right? and I would say it's about 10,000, or even if we gave it 100,000, okay, products, that's big enough. But it is still much smaller than 1.6 billion, right? And we have 6 columns here. And for the time, if we take each day, if we take day as the unit time, then we would have 365 days times, say here we have 6 columns. Okay. So what you would have is you plus this 4 numbers together. These are the space you need for the star schema, right? And you can compare with if you use the universal schema. So roughly speaking, it would be just 1/4 total space of, if you use the universal schema. And if we consider the space that we need for different attributes or different columns, this number can be further reduced. So this is why we use this star schema, because it can save a lot of space. And also, by using this star schema, we kind of decompose the whole table into a fact table and a set of dimension tables, right? And the whole thing becomes more clear. And later, when we do operation like roll up or drill down or pivot or slice on a particular dimension, we can do the operation on the specific dimension table. So we don't need to touch other tables, right? We only need to look at the corresponding dimension table and the fact table. So that's the thing, right? Yeah. So we do have other kinds of schemas, which are just the variants of the star schema. We will have a break and we will continue introducing these topics.